Okay, so let's get started. According to some friends, I talked a bit too fast from the previous videos, so I will try to talk as slow as I can for the in the future videos. And it wasn't a very good explanation for question number three, so I'll probably try to redo it if I had time in the future. And well, I probably talked a little bit too fast again. And according to some friends, the color wasn't pretty, so I would probably switch my color a bit to advanced. Lord, is there a usable color? Do you think this looks good? I hope this looks good enough. Just try black. Yeah, sure. Okay. So as you can see from the question, let's go through the question first. So this is the exam paper of I should cancel this first of exam one in 2015, the fall semester, and we're on question number four. And what is the lowest frequency of light that is required to move an electron from a sample of titanium metal if the binding energy of titanium is 3.14 times 10 to the power of 3 kilojoules per mole? So as you can see, Dr. Ma used his old trick that it wasn't in it says what is the lowest frequency of light over here, and then it used the kilojoule over mole over here. So this is a very common trick that Dr. Ma used in his exam. So if you want to improve your grade in a very short period of time, please pay attention to what the question asks. Dr. Ma is really good at using these uh, weird tricks to trick hardworking students, like my roommate. Never mind. So first, let's do a dimensional analysis for this particular data over here to make it more friendly for the upcoming manipulations. So it's 3.14 times 10 to the power 3 kilojoules over 1 mole. I'll do an American style dimensional analysis, which, no, it's not an equal sign over here, which we want to convert it to like for each photon, since that's what we're going to get, since we're going to calculate for the question. So it's 1 mole, and this is 6.02 times 10 to the power of 23 photons. And if you remember it correct, this is the Avogadro's number, and we will get 5.214 times 10 to the negative 21 kilojoules per photon. Yes, I did my calculation ahead of this time, so I'm proud of myself. Never mind. And which is, if you're fine with math, you should be able to get quickly that this is exactly the same thing, but 1,000 times joules per each photon. And so there is a formula on your formula sheet. If you remember it, it says the energy of the ejected electron. I will not write out the entire word electron. For each electron is equals to the energy of the light, which is the Planck's constant times the frequency, minus by the given binding energy, which is the data over here. Let's circle it out. So this term, wow, this black looks really cool, and is exactly this term. But I guess it kind of interferes with the other stuff. I probably try to make it less appealable. Like, I hope this works better. And let's keep going. So, and since it's asking for the lowest frequency, which means that the light is just has enough energy to kick out the electron without giving it any additional energy, which will give us 0 equals the energy of the light minus by the binding energy, which will give us the binding energy equals the energy of the light, and the frequency will equals to the binding energy divided by the Planck's constant, which is the number we get over here. It's the 5.1214 times 10 to the negative 18 joules per photon divided by 6.626 times 10 to the negative 34 joules times seconds, which is the Planck's constant. It's on your formula sheet. Yes, it is on your formula sheet. And that exactly equals to 7.87 times 10 to the 1/15 1/2, which this term, if you remember from the previous videos, it's hertz. So they're exactly the same thing. So as you can see, this answer is exactly answer number the A term, which is the correct answer. Okay, that's it. Let me switch it out.